Okay, it's a great pleasure to be here. I'm very thankful to the organizers for the invitation, and it's wonderful to see this new science town being erected here and basically completed in a beautiful place. Okay, so a few words about Spenta. I think I met him for the first time in Princeton sometime, but even before then, I heard about his work, and actually there is a great deal of synergy between what we've been doing for over 30 years, actually dating back to the Schwinger model in the mid-'80s, effective chiral Lagrangians, and I've been very strongly influenced by Spenta's work. So let me mention a couple of examples which are maybe not the best known. One is this double trace paper by Dast, Harris, and Gupta and Wadia, which I thought was wonderful, and I pretty soon followed up on it. And actually, the double trace story has been one of the big currents in my research too, but it kind of dates back to this paper, where they ascribe double traces to kind of touching interactions between spheres. And of course, there was a lot of work in parallel between us on the C=1 matrix model. And now my talk today will kind of indirectly touch on two-dimensional black holes. So actually, I prepared these right before David, but let me say the same thing. Spenta and I, and now, of course, David, also share a passion for large N theories. So this is, the large N theories is a major topic of the talk today. So the talk is mainly on this paper in collaboration with my outstanding graduate student, Grisha Tarnopolsky. And the slides would not look like this without him. You'll see a whole bunch of colorful diagrams. Okay, so large N limits. This has a lot of common points with what David said, but it's a very important theoretical tool because some models there is no other expansion parameter than 1/n, and there are sort of, until recently I thought there were two broad classes of models. One are the vectorial large N limits where actually there is a double trace interaction. If you have a vector field, the only type of interaction you can write down is double trace. Then it's exactly solvable via the Hubbard-Stratonovich auxiliary field, and there is a broad class of models of this type. Then there is the famous Hooft large N limit, where we go from vectors to index objects to matrices, and now you can write single trace interactions, of course. And as we all know, you then get planar diagrams. So here is an example. One of the inventions of Hooft was this double line notation where, for example, for an adjoint matrix, you have one line running this way and another one running the opposite way. And the goal is to count index loops. So you have to count index loops. And this, for example, has, compared to the free propagator, has an extra factor of g² from two vertices and an n from the index loop. So you have to take the large N limit, keeping this g² n fixed. Now, in general, these models are not exactly solvable, but there are some special cases like the C=1 matrix model, where you can, for example, have these more complicated planar graphs, and again, you can count up the loops and see that, for example, compared to the leading free loop, which gives you n², this gives you n² times g² n². So the whole trick here is how to count the two-dimensional topology. And so actually, the few people know that the archive was born out of a small mailing list of people who were emailing papers to each other. And I think both Spenta and I were on the same mailing list. So one of the great spin-offs of the matrix models was the creation of the archive. And the other one was the creation of tensor models, as we'll here in a second. So the matrix models, of course, as already alluded by David, can be thought of as a way of solving two-dimensional quantum gravity. So the trick is there to tune this coupling kappa to a critical value where the planar Feynman diagrams become large. And so the dual graphs to the Feynman graphs are just these triangulated random surfaces. And so both Spenta and I had great fun working on all kinds of aspects of this exactly solvable model where the eigenvalues act like free fermions. And one of the dreams was to say something about two-dimensional black holes which were discovered in two parallel papers, one by Mandalson, Gupta, and Wadia, and one by Witten. But somehow one of the frustrations of this C=1 matrix model that somehow it seems to have fallen short. I mean, there were certainly interesting works on that, but there is no crisp conclusion about two-dimensional black holes. So now, as we already heard from David and Subir, there is renewed hope to say something about two-dimensional black holes using somewhat more complicated models. So before I proceed to those models, I just want to make a very simple point that, for example, in this model, there is just a single gauge group symmetry, SUN. But it's no trouble, or you can make it SON, as was already mentioned in one of the questions, and then you also get non-orientable surfaces in addition to orientable ones. But there is another way to write the matrix where you treat the two indices as distinguishable. So the first index belongs, say, to one ON and the other one to another ON. And then this makes the model more restrictive, the extra symmetry. In particular, you cannot have a cubic interaction now. You can only have a quartic interaction of this type, MM transpose and M transpose trace. And then the propagators are represented by colored double lines where, for example, there is a red line and a green line, and the vertex pairs them up in this interesting way. Now, as far as two-dimensional planar graphs go, there isn't a huge difference. You still actually get a kind of model of planar graphs. But if you look at the details, you see that there will be red loops alternating with green loops. So if you look at the dual lattice, which is always can be thought of as squares. So now you build up a random surface of squares connected in intricate ways. But now the different vertices of the square are not completely the same. Like the vertex that sits at the center of the green loop is a green vertex, and the one that sits at the center of the red loop is a red vertex. So each square has vertices that are alternating, red, green, and when you glue these squares, you cannot glue red to green. You only have to glue them in 2 of the 4 possible orientations. So that doesn't seem like a very big deal, and you can enumerate them. In this case, there isn't a huge difference. But now let me make the big leap, basically, from bifundamentals to trifundamentals. So now let's imagine that we have some 3 tensor with 3 distinguishable indices, and the first will cover a color as red, the second is blue, and the third is green. And then you just think of it as the symmetry group as ON cross ON cross ON, okay? And then the propagators will be just triple lines, and the triple lines are colored. And the vertex will be this type of contraction, which we call the tetrahedral contraction for reasons that will become clear in a second. You see that every pair of fields have only one index in common. This is the rather non-trivial feature. You can write another interaction where, and this necessitates the 2 blue lines crossing under each other, right? You could also arrange it so that this blue line goes like this and this goes like this. Then there will be 2 indices contracted between 2 of the fields and 2 That's not the basic one. That other one we call in our lingo the pillow interaction because it leads to so-called pillow graphs. But let's for now just talk about these tetrahedral graphs. So the claim is that this theory leads to a totally new large n limit. At least it's, well, it's the one that's encountered in SYK models, but it was very little known until recently. And then the scaling limit, you have to keep gn to the 3/2 fixed, unlike, for example, g squared n and the Hooft limit and things like that. And I want to explain why this is. I think this is pretty remarkable, and as both David and Subir stressed, I think it really opens a whole new range of possibilities. And this was, in some sense, already known to Gurau and collaborators for several years, but there was little tunneling between these two disconnected communities. And Witten, actually, in a paper he posted on the Halloween day, October 31st, managed to connect the two. And this immediately resonated with me. So I basically dropped everything. And as of 8:30 p.m. Eastern time on the Halloween day, I've only been thinking about this. And I think it solves some very interesting issues about gauge gravity duality for SYK model. And I'll try to explain why I think that. So first, let's just think about, so here I denoted these as phi, so you can just for fun consider bosonic theory. So phi is a scalar field. So this is just a variant of a 5-4 theory, for example. And you can study it in 4 dimensions and 4 minus epsilon dimensions. And in particular, you can start counting n's in various graphs of 5-4 theory. And here is, and then the game is pretty clear. You want to write the graphs as triple lines and count how many index loops there are. When you, for example, here is a very basic graph where there are 2 vertices, and there is a way to contract index loops so that there are actually 6 of them. And this is rather non-trivial because in each vertex, the blue lines pass under each other. But here they pass under each other again so that there is still 2 blue loops. And there are 2 red loops and 2 green loops. So there is a power n to the 6. And this, in this scaling limit I defined, is just n cubed lambda squared. But this is exactly what you want, because the leading free graph obviously gives n cubed. And now this graph is already starting to look like melons. This one is not obviously a melon. But this one looks like more like watermelons. People always ask me, where are the melons here? Basically, these things are striped. And in the Q interaction one, you'll have Q lines. So you can get a nice striped watermelon. OK, so now you color these, and you find a 9 index loops. And then, again, everything works out. But these are actually exceptions rather than the rule. Most graphs, you cannot do this. They cannot give you this nice power. They're actually always smaller power. So only these so-called melonic graphs are of this type. And actually, the initial interest in the subject that dates back to the golden era of matrix models, 1991, had to do with basically thinking about dual graphs. And the dual graphs, so in the matrix models, the dual graphs were just like triangles or squares. Here, you really need tetrahedra because you need to keep track of the 3 colors. So when a line passes through, you need a triangle as a dual to keep track of how these 3 strands are oriented, or 3 wires. So this graph is, for example, 2 tetrahedra glued along the face, and then the other faces are identified, and so on. So this was initially not this model, but a similar model was advocated as an approach to 3D quantum gravity. And this is the history. There were 3 initial papers by Ambjörn Jonsson, Sasakura, and Gross, who basically, they basically did the right thing. Actually, if you read these papers, they already had this formulated. They had the tetrahedral interaction. The only subtlety they missed is that you wanted to treat the indices as distinguishable. They tended to just think about a single ON group or single UN group. And then it just was impossible to analyze the powers of n in this case. it seems like a technical subtlety, but and then Razvan Gurau and initially had a breakthrough, and then with Rivasot and others, they found various models with multiple symmetries that do the job. And initially, he dealt with a so-called, what he called colored model, which has ON to the 6 symmetry. And I'll explain in a second why. But in the model that I'm mostly talking about, that's the one that Tarnopolsky and I used. We call it the uncolored model, but it really still has 3 separate index colors and 3 ON gauge groups. What you cannot live with is a single ON gauge group. And it will become clear in a second. So basically, you can just think about gluing these tetrahedra, and then the equivalent way in the dual lattice are these melons, the Melonic graphs. Sometimes you have trouble seeing where the melons are. For example, as David showed, there is this sort of ladder with rungs, and the melons only sit at the end. But these are still Melonic graphs. And remarkably, they may be summed explicitly, so this Melonic large N limit is exactly solvable. So I always thought, I was seeing these tensor model papers, but I didn't have much hope, because I thought from vector models which are solvable to matrix, like adjoint models, which are in general too hard, like large NQCD, that's already a huge step in difficulty. Then you go up to 3 index, 4 index, you're going to get some horrible mess. Not so. You drop back to, again, solvable models in a certain limit. But the price you pay is that the dual structure of these glue tetrahedra is basically dominated by these ladders of branched polymers. So it doesn't seem very interesting for 3 geometries. And that caused a lot of consternation in this community. But now let's just forget about the 3 geometries. Let's just think about them as a new way of doing large N. Okay, and then it actually is very nice. But then what about non-Melonic graphs? Well, here is a simple graph, like with 3 vertices. You start sketching the colors, you immediately realize that you cannot have something that survives in this large N limit, because the blue loop is just a single loop. There are still nice red and green loops, but there are too few blue loops. So this is actually suppressed by N to the 3 halves. Okay, and this N is what David called little n. Okay, from the point of view of the SYK model, the big N is like little n cubed. So given this scaling, it's easy to see that none of the graphs with an odd number of vertices are Melonic. Only very select few of the even number. Here is actually, if you read the book by Kleinert and Schulte-Frohlinde on 5-4 theory, they have nice lists of all diagrams of 5-4 theory. And you can ask which ones of them are Melonic. So, well, the first one is, but none of the odd ones are. And here only this one is. 6 other graphs, only 2 are Melonic. And then it gets even worse. So instead of the n factorial growth, you have a much, much slower power growth. And that's the secret for why this Melonic limit works. And now here is the punchline. Why do you need multiple gauge groups? You need them because, and this is really the main breakthrough of Gurau and collaborators, is that you have to start sort of, when you have this 3-colored graph, you want to count the total number of loops. So let's first erase all blue loops. Then we have the usual double-line Hooft graph with red and green loops. And then we can count the number of loops using just the Euler characteristic. So in this red-green graph, you have the number of loops. FRG is just chi RG, the Euler characteristic of this graph, plus the number of vertices. Then you do the same for the, for the other 2, and then you add them up. You add them up, and of course, FRG is FR plus FG, is the number of red plus green loops. You add them up, you get twice the total number of loops. And this is just this beautiful formula, 3v over 2 plus 3, minus the sum of genuses of these 3 dicolored subgraphs. And then, of course, genus cannot be negative. So this immediately puts a bound. And you see that if the maximal graphs with the biggest power of n are where the genus is 0 for each of these subgraphs. And then f total is 3 plus 3v over 2. And then the whole power is like this, as advertised. So you see that these graphs where all the subgraphs are genus 0 are the ones that we want. So this is, and then this sort of generalizes to the Q case. But the big leap is already from matrix models to these 3 index. The matrix model is totally different, and you see that this fails. This doesn't work. But okay, so this shows that why this is so nice. And there's a brief digression, actually, that many people have noticed that this n cube is somehow related to the degrees of freedom on M5 branes. And it's still mysterious why this is. We actually, back in '96, speculated that this has to do with some kind of 3 index objects, maybe M2 branes with 3 boundaries that can attach to 3 different M5 branes at a time. And this was developed by Kim Young Lee and collaborators, but it's not totally clear yet what, maybe some kind of souped-up supersymmetric version of these tensor models can describe M5 branes, but we don't know. Now, this was extensively reviewed in the 2 previous talks. You have the random interaction with the same type of Melonic graphs and random couplings. And the model flows to strong coupling where it becomes nearly conformal, as was shown by Georges Parcalet, Sachdev, and subsequent works. And then, so now Witten realized that the same Melonic graphs follow in this these class of tensor models. He used what people call colored. I would call it maximally colored. And you'll see in a moment why. Basically, there are 4 separate fields, psi A, A, B, C. And the model actually has On to the 6 symmetry. Each of these fields is trifundamental under some 3 groups out of these 6. So you can call it, this is sort of what David already showed. You can think of it as a tetrahedron. The interaction is like a tetrahedron where each edge has a different color. And each edge corresponds to a different On group. So now concerning the spectrum of operators, gauging the symmetry removes the non-singlet states, and in particular removes the fermions. So the puzzle of what to do with fermions and the SYK model in the gravity dual is solved by this model. So even before you go too fancy, just gauging this gauged model, I think removes the non-singlet states. And I'm always used to only singlet states. So then this model becomes like just a very standard gauge gravity duality. And then, so with Grisha Tarnopolsky, we tried to write down, actually, this Gurau-Witten model doesn't even seem to have exactly the same number of two-particle states as SYK. It's maybe closer to generalized SYK of Gross and Rosenhaus, because you can write down more complicated bilinear ones. But initially, Gurau just played with these type of models, but then people realized that it's enough to have like simpler models with fewer gauge groups as long as it's more than 1. And this model with On-cube symmetry, we started playing with it, but then we realized, it was pointed out to us that a few months ago, Carrozza and Tanasa studied a 0-dimensional model with these symmetries. But they certainly didn't think about quantum mechanics and fermions and things like that. So we wrote down this model, and it also has a lot of nice features. The interaction can be thought of like this. It's again a tetrahedron, but now there are only 3 separate colors. And you can see that if you look at the tetrahedron, it's the same as this, right? Topologically, it's basically each field has 3 colored lines going out of it. And you see why you must have two blue lines cross under each other, because in a tetrahedron, they must cross under each other. So then you build up these lines. Can I have a few more minutes? So you have, and then you just build up these colored triple line graphs. You use all this machinery, and there you go. So now, concerning gauge invariant operators, there are certainly the same gauge invariant operators as people studied in the SYK model. Here they assume this form, where n is odd. So that part of the analysis essentially carries over. But there is also a multitude of gauge invariant multi-particle operators, which can be visualized as these glued tetrahedra, right? So, and you can grow them in all directions. So there seems to be a vast number of these additional operators. They should be dual to many additional fields coupled to the two-dimensional gravity. Now, so one thing Grisha and I did is we worked through the same analysis that David already reviewed. It's a completely identical, after some trivial transcriptions, to what was done in the SYK model. You solve these beta salpeter type equations for 2-point functions and 4-point functions, and you, so this is the analysis of a certain 3-point function by Gross and Rosenhaus. You have to find the eigenvalues of a certain kernel and then solve the equation g of h equals 1. That was already basically done before us. We just redid it. You get this graph with these modes, and this famous h equal 2 exact mode, that's like an L minus 2 acting on the vacuum. That just shows to you that this is like the analog of stress tensor in say, 1+1 dimensional CFT. So that's why we're so excited about this model and think that this is dual to gravity. But then there are higher scaling dimensions. But then there is some vast number of additional stuff which we're now trying to study, actually. And then there is, for example, other variants, like complex fermion model with psi-psi-bar interactions that has un squared cross ON. This one has the additional feature that now you can have an even number of derivatives. And in particular, there is an operator psi-bar psi in this model. So we solved for this translates into looking for symmetric eigenfunctions rather than anti-symmetric ones. And here is the full spectrum. So the first symmetric one is this one. And you see that it's actually a lower one. It has a lower scaling dimension. But everything hangs together, and this is another nice model. Now, Bosonic tensor models, that has a feature that was already pointed out by Ambiorn et al. That this is not positive definite. So it's not clear if these models are stable, but the model can still be solved using the same machinery. And we realized that it actually, again, has the same h equal 2 mode, which is quite non-trivial. So it's, again, a bit like formally it's a conformal quantum mechanics. So what's the problem with it? It seems like the leading solution, the one that you had here sitting at 1.22, becomes complex. And complex means that the CFT is really unstable. In other words, in the dual ADS space, there is a mode that violates the famous BF bound. But you can still formally study it. And then, so here is a picture of higher gauge invariant operators. They can be viewed in dual pictures, just gluing tetrahedra in all possible ways. And I think that's a crucial new feature of these models. And one can study super melons, like supersymmetric Melonic theories. So finally, the conclusion. So we saw that early exploration of the random tensor models was to study discretized quantum gravity. But then a breakthrough occurred for these models with multiple gauge groups, which were shown to be giving new solvable large n limits. And recently, it all merged together into a picture with SYK models and tensor models on two sides. And the crucial thing is this h equal 2 mode, which is responsible for gravity. So maybe we will come back and finally say something about the two-dimensional black hole that Spenta discovered in '91. So thank you.
So in the non-gauged models, is it clear that the ON symmetry is not broken in the saddle point? Or maybe that's related to this instability you just
I think it's more or less by definition. Like certainly in the fermionic models, you just look for wave functions, and the wave functions will fall into representations of ON cube. And you just are supposed to look only for the singlet ones, but they organize into that. In the bosonic model, it's just less clear if it makes sense for finite n. But the fermionic model, I think, is perfectly well defined at any finite n. It clearly is ON cube symmetric or ON to the 6 symmetric. And then all that gauging does is it just throws away all the wave functions with multiplicity. So I think that part is under control.